Hey guys, welcome back. We're doing the titrations and we are doing a strong weak. So we got strong weak. All right. So we have, in this case, a weak acid of acetic acid titrated with the sodium hydroxide. So the sodium hydroxide is going to be in the burette, which makes it the titrant. And the acetic acid is in the flask, which makes it the analyte. All right. And so we're going to find the pH at these 4 points again. So we have the initial, we have before equivalence, and past equivalence. So those are the 4 regions we're going to talk about. So for number 1, the initial, it's the pH of a weak acid. Well, what does that mean? That means we have to do the ice table. All right. And so we're going to have, for 1, weak acid, you have CH3COOH plus water, hydronium, and CH3COO minus, right? And these are all have state symbols that are important. All right. Do your ice table. Initially, we have 0.1 molar. Minus x plus x plus x. So we have 0.10 minus x, x, and x. And our Ka expression here is hydronium, acetate, and acetic acid. Now, if you wanted to shortcut this, you can still do, I would still do H3O plus, A minus, and HA. You can do that here, right? This could be HA, and this could be A minus, and that makes it faster to write. If that's something you're interested in doing, you feel free. If you want to use the real chemical formulas, feel free. All right, so we now know Ka, all right? You'd have to look up Ka, or it's provided. And I'm going to provide it for you now. Ka is 1.8 times 10 to the negative 5 for acetic acid. So we have 1.8 times 10 minus 5 equals x squared all over 0.10 minus x. You can approximate here, right? And that approximation makes this x go to 0, right? We're approximating the change is negligible. So that means we get 1.8 times 10 to the negative 5 equals x squared all over 0.1. Or 1.8 times 10 to the negative 6 equals x squared. Which means if we take the square root, x, which is the concentration of hydronium, is 0.0013 molar. And again, the pH is negative log of our hydronium. So the pH is negative log of 0.0013. And I'm getting 2.89. Hopefully you're getting the same number. So that is how we do number 1, just like a weak acid. It's just the same. What's the pH of this 0.1 molar weak acid, or whatever the concentration happens to be? Part 2, we're adding our base. Oh, that's not level. That bothers me. There we go. All right, part 2. So now we have to figure out, we have 40 milliliters of CH3COOH. We know for every 1,000 milliliters, there's 0.10 moles. So that means we have 0.004 moles, or 4 millimoles of CH3COOH. And now we have 20 milliliters of our sodium hydroxide. And we got for every 1,000 milliliters is 0.10 moles, which is 0.002 moles, or 2 millimoles of hydroxide, because we're not caring about the sodium. Why not? Well, let's write the balanced equation. You would have CH3COOH, acetic acid. We have sodium hydroxide. You have hydronium. Well, actually, you don't have hydronium. We'd have sodium acetate. H3COO. And water. There we go. Well, net ionic equation, we know that this is weak. All right, so it stays together. Sodium hydroxide strong. So we know it's going to break apart there. All right. Strong, it's ionic. And aqueous, so it's going to break apart. And liquid. So my only spectator ion is sodium. So my net ionic equation, our net ionic equation, would be acetic acid plus our hydroxide with acetate and water. Now this is a lot of times where I draw a sad face because we have hydrolysis here, okay? A lot of times in class we'll do the ice table. And we have what? We have 4 millimoles here. And we have 2 millimoles here. And 0. Well, let's go with this color, 0, right? And we just do it minus 2, minus 2. A lot of times we just leave it there and we go through this in class. But what happens is you have a plus 2 here. So we have 2 millimoles of acid, no hydroxide, but we have 2 millimoles of conjugate base. New volume. We have our 40 milliliters of our acid. And we have our 20 milliliters of our base to give us a total of 60 milliliters. So if we do our 2 divided by our 60 milliliters, well, that's, yep. So we get 0.033 molar acetic acid and our 2 millimoles divided by our 60 milliliters. That's going to be 0.033 molar acetate. All right, so and this is before the equivalence, all right? And because we have acid and conjugate base in solution, that means we are in the buffer region. We can use Henderson-Hasselbalch. All right. So if we use Henderson-Hasselbalch, right, remember that is pH equals pKa plus the log of your conjugate base. In this case, it's acetate all over acetic acid. So our pH would equal the negative log of our Ka of 1.8 times 10 to the negative 5 plus the log. Well, we have 0.033 all over 0.033. This is 1. The log of 1 is 0. So then the pH is just equal to, so where are we at? So the pH is equal to negative log of 1.10 to the negative 5, which is 4.74, right? And since we are halfway to equivalence, the pH equals the pKa. That's important, all right? That's always good to know. So when you're halfway to equivalence, which we have, if you look at this, we have, right, 2 is half of 4. So we're halfway to equivalence, all right? And so anytime we're halfway to equivalence, the pH equals the pKa. Always, all right? Now, the worst part about this, part 3 here, is equivalence. All right, and so for equivalence, we're going to have 40 milliliters of sodium hydroxide. And we know we have what? Every 1,000 milliliters, 0.10 moles. So it's 0.004 moles or 4 millimoles of hydroxide. Net ionic equation again, right? We have CH3COOH plus our hydroxide. And we have acetate. And we have water. And again, I always go back to the original of 4 millimoles. All right? Go back to the original, just in case we don't want any error propagating through our calculations. Then we have 4 millimoles. And we have none. Limiting reactant, -4, -4, +4. So we have no acid, no base, but conjugate base we have 4 millimoles. We have a new volume. That new volume, we started with our 40 milliliters of acetic acid, and we added 40 milliliters of base. So our new volume is 80 milliliters. All right? Yes, 80 milliliters. All right. So if we do this, 4 millimoles divided by 80 milliliters, that means we have 0.05 acetate. So now the question, what do we do now? Is the pH 7? Is the pH 7 because of this? So is it 7? No. No, it's not, because we have that. So this is the same now as a question. If we had a new question, What would be the pH of a 0.05 molar solution of acetate? That's the new question. So the pH is due to the hydrolysis of the conjugate base. So our acetate plus water, we are going to make acetic acid and hydroxide again. So because of how this system works, right, we're going to make some hydroxide. And so if we have an ice table, right, we're going to start with our 0.05 molar. And then we got 0 and 0 minus x plus x plus x. So we have 0.05 minus x, x, and x. Kb, in this case, would be your CH3COOH hydroxide all over acetate. Now, how do we get the value of Kb? Because in this case, it would not be given to you, would it? All right, so let's think about that a second. Kb, if you remember, Ka times Kb is Kw, right? And so Ka is 1 point times 10 to the negative 5, Kw, 1 times 10 to the negative 14. So Kb is Kw divided by Ka, right? So Kb is 1 times 10 to the negative 14 over 1.8 times 10 to the negative 5. So Kb is 5.6 times 10 to the negative 10th. All right, our Kb expression, so 5.6 times 10 to the minus 10 equals x squared all over 0.05 minus x. And because we are more than 1,000 times, right, we're quite more than 1,000 times, 10 to the 8th times, right, we can approximate that change to 0, right? So approximately the change is negligible. So that gives us 5.6 times 10 to the negative 10 equals x squared all over 0.05, right? We're going to approximate that. And so if we do that, so 5.6 times 10 to the negative 10th times 0.05 is 2.8 times 10 to the negative 11th equals x squared. And so 5.29 times 10, so 5.3 times 10 to the negative 6 equals x, which is the concentration of hydroxide. All right, so now we know that pH plus pOH is 14. So that means the pH would be 14 minus the pOH. So the pH is 14 minus negative log of hydroxide. That means the pH is 14 plus the log of 5.3 times 10 to the negative 6. So pH, I'm getting, hopefully you're getting the same thing as 8.72. All right, so that's what I'm getting for 3. Wow, that was a lot. And finally, 4, which is past equivalence. So how do we know that? Well, we have 60 milliliters of sodium hydroxide. For every 1,000 milliliters, we have 0.10 moles. So, well, we want to do 0.006 moles, or 6 millimoles of hydroxide, right, from our NaOH. Our net ionic equation, CH3COOH, AQ, plus hydroxide, CH3COO minus, and water. So in our ice table, what do we have here? Well, we're starting off with 4 millimoles and 6 millimoles and 0 millimoles. Who is limiting? Well, looks like the acid. -4, -4, +4. So we have no acid left. We have 2 millimoles of hydroxide, and we have 4 millimoles of conjugate base. So now we have a new volume coming, don't we? And that new volume would be our 40 milliliters and our 60 milliliters to give us 100 milliliters. All right. And so in our 100 milliliters, so let's do this. 2 millimoles divided by our 100 milliliters. So that means we have 0.02, right? Then we have our 4 millimoles divided by our 100 milliliters. And that would be 0.04. Now, pause. Let's look at this. 0.04 molar acetate. All right, so we're going to look right here at the 0.04 molar acetate. And we're going to look up here at the previous example. At the previous example, we had 0.05 molar acetate, which is a little bit bigger, right, than 0.04 molar acetate. Well, 0.05 molar acetate produced 5.3 times 10 to the -6 molar hydroxide, right? So if you follow my logic here, this much conjugate base produced this much hydroxide. Let's assume that 0.05 molar and 0.04 molar are going to produce the exact same number. All right? My question to you is, if I add this number to the 0.02, what do we get? Well, if you type in your calculator, you're going to get 0.02 and then some zeros. A few zeros and 5.3, right? So what we can do is pass the equivalence point right? You can ignore hydrolysis of conjugate. In this case, it's a base, right? But it depends on what you're doing. If you're doing a strong acid, weak base titration, it'd be the conjugate acid. But in this case, it's the conjugate base. So that means the pH is, because the pH is due to excess hydroxide added from the titrant. Okay? All right, hopefully that makes sense. Now, obviously, if you're a drop past the equivalence point, yes, you probably will have to do it. At this point, I have not calculated that or made a student calculate that. So, I will not make you do that. All right. So that means the pH plus the pOH is 14. So that means the pH is 14 minus the pOH. That means the pH is 14 minus negative log of our hydroxide concentration. So the pH is 14 plus the log of 0.02. Means the pH, I'm getting 12.3. All right, so let's recap this. All the way up. A lot of work for this problem, isn't it? So, strong, weak. In this case, it has to be a strong base in the burette and a weak acid. The same principles hold true whether it's a strong acid and a weak base. It's just going to be opposite, all right, with the pHs. So you got to have Ka. So the initial is just the pH of a weak acid. Do your concentration, your ice table, Ka. Whether you can approximate or not depends on Ka and the initial concentration. And you get your pH of the acid, all right, the initial pH. Then we start adding from the burette, all right. So we had our initial amount of acid, our initial amount of base. We found our initial moles. We have our net ionic equation, all right, and we got hydrolysis going on. So, but we are before equivalence. And so we have in solution acid and the conjugate base, which means it's a buffer, right? So we can use Henderson-Hasselbalch here to calculate the pH, and we did, because in this case since we are halfway exactly to the equivalence, the pH equals the pKa. Equivalence. So strong, weak, that's a sad face, all right? So we found out how much sodium hydroxide we had, which was 4 millimoles. So it's equivalence. And you can see right here, it is equivalence, right? And we make 4 millimoles of our conjugate base in this reaction, and which is, in this case, 0.05 molar with our volume, because our volumes are additive. And the pH is due to the hydrolysis. So we do our ice table of the conjugate base. So the question might as well have just been, what's the pH of a 0.05 molar acetate solution, right? Sodium acetate solution in this case, all right? We knew what Kb's expression was. We remember Ka times Kb is Kw, right? So we calculated Kb, then numerically. We put it into the ice table, got our expression for Ka, found that X was hydroxide of 5.3 times 10⁻⁶, which then we just did pH, right? pH equals plus pOH is 14. Rearrange, solve for pH 8.72. Past equivalence, we can ignore hydrolysis. All right? So past equivalence, we can ignore the hydrolysis. Right? It's only due to this excess base, because this 0.04 molar does not contribute enough. It contributes, but not measurably. All right? Okay? And so we just did the same pH, just like a strong, and got 12.3. So hopefully that works for you guys. If you have any questions, reach out. Otherwise, we'll see you next time. Take care.